Like Kartik introduced, my name's Divyam. I'm the systems interface lead for the team. This presentation will be a bit of a look into our 2019 vehicle, TED3, a lot of the engineering and design behind the specifics of it. And then Brad will also talk a bit more about the engineering management that we had to do to achieve such a great design. So let's start off by introducing the car that's going to be the focus of this session, TED3. TED3 is Western Sydney University's fourth vehicle and was built to compete in the 2019 Bridgestone World Solar Challenge. It's a four-wheeled, monohull or bullet-shaped vehicle. It uses 2.4 square meters of gallium arsenide solar cells, a Moran-designed high-efficiency motor, and a 20-kilo lithium-ion battery pack full of 18650 cells. It has a fully carbon composite air body and chassis with a primarily machined aluminium suspension. It was able to travel around 400 kilometers on just the 20 kilos of battery alone and can travel at approximately 70 kilometers an hour on solar alone if exposed to full sunlight. It was the first car that the team have made primarily in-house, with nearly 80% of all components and nearly 100% of all composites being manufactured at our Kingswood facility. The greatest achievement of this vehicle was that it broke the record for the lightest ever solar car to compete in the Bridgestone World Solar Challenge at only 116 kilos race ready. It is also, as far as we know, the lightest road registered car in all of Australia. The first thing I want to talk about is the aerodynamics of TED3. Solar cars in 2019 were split into two distinct classes, monohulls and catamarans. TED3 is a monohull shaped car, which means that all of the tires and the driver is encased in one single hull. Due to this and the incredibly narrow track width of the front tires, it has a very low frontal area. The bottom of the car is very flat and very low to the ground, around 50 millimeters, reducing turbulence generated by any exposed wheels. Since the car uses gallium arsenide solar cells, which are of a space grade quality, meaning they're very, very efficient, it only needed 2.6 square meters of the solar collector area. Compared to other monohull cars at this event, TED3 had no overhanging solar area ahead of or behind the vehicle, and it achieved this by flaring the main car body outwards near the top on either side of the driver, as you can see in the image. This created more solar area while still keeping the car as small as possible. It also creates geometry that helps stability under crosswind. The car was designed with a zero lift philosophy where it produces as close to net zero vertical forces as possible. We did not want any downforce to increase rolling resistance or any lift that would make the car unstable at high speeds. Any lift or downforce created also generates associated drag, and this philosophy helps reduce straight line aerodynamic drag. The car is also designed to have extremely sharp trailing edges to reduce the amount of separation caused off the back of the car. To achieve this, both the end of the carbon air body and the end of the vacuum formed canopy have a 3D printed insert that creates a razor sharp trailing edge. All these design decisions combined, we believe to have created one of the most aerodynamically efficient solar cars at the 2019 challenge. The chassis of TED3 is also very unique in that it's not a monocoque. Most other solar cars and all of our previous solar cars have been of a monocoque chassis in which the outer skin or shell of the car is structural. However, TED3 had the driver, suspension, motor, and battery all in one very tight package, very close to the center of the car, and an aero body that was very far away from all of those loads. To create a monocoque structure in this configuration would have been very heavy because it would have to transmit forces over a very long distance, and hence a separate chassis and aero body were made. The aero body, as seen from the outside, is everything that is externally open to the air, all of the red bits of the car. This entire piece is non-structural and only acts to deflect wind efficiently around the car. Using spars, this aero body is connected to the main chassis, which is what you can see in the images on this slide. The chassis is created to a near perfect 50-50 weight distribution, with the center of weight of the driver right in the middle of the car's wheelbase. The battery is also located right behind the driver's back, separated by a firewall. All the mass is held, all the mass held in the chassis is designed to be as low to the ground as possible, creating a very stable car at high speeds. The entire chassis tub is designed to take a 5G impact load from the front, the side, and the top, while still keeping the driver safe. It has a 5-point racing harness and a fully integrated carbon roll hoop. In fact, the whole chassis is made out of composite material. We use woven, bidirectional, pre-impregnated carbon fiber that sandwiches either Nomex honeycomb or a foam core, depending on the area. Any place where a bolt goes through the composite, we ensure to have foam core and not honeycomb. We also use patches of unidirectional carbon fiber, where we know strength in a specific loading direction is needed. Even the suspension mounting points on the chassis are carbon fiber ears. These have been tested on an Instron machine and have taken upwards of 25 tons of impact loads at high frequency without failing. The front half of the chassis is a molded tub, whereas the back half consists of flat panel sheets that are water jet cut to the perfect shape. All glue joints within the chassis are made using an aerospace-grade adhesive called Sparbond. The final chassis tub alone weighs just 15 kilos, and we think this was a pretty incredible achievement. When we first measured the chassis, we really did think that we had one very competitive car on our hands. Next, I want to talk a little bit about the suspension design. The front and rear suspension in TED3 are of a double wishbone configuration. They have an upright joining them and use transverse mounted shocks and a bell crank and pull rod system to connect them to the sprung mass. This was done mostly for packaging reasons. So for the front suspension, the way to imagine it would be the wheels are on either side of the driver's legs, and the shock are mounted sideways in the car and run below the driver's knees and are connected to the main suspension using a pull rod. This allows the wheels to come closer to the driver's legs and allows for a narrower air body. It also allowed the design to achieve a near 1-to-1 motion ratio. The entire suspension geometry is designed to create as little rolling resistance as possible. The most important way to do so was using stiff shocks that don't waste too much of the car's energy while still providing a stable ride. We partnered with Bilstein to create these amazing one-off aluminium body shock absorbers. The rest of the suspension geometry is designed to have zero toe and zero camber to reduce rolling resistance. Furthermore, it's designed to have as little camber and caster gain as possible, as well as bump steer throughout the actuation, while still fitting inside the air body. After the geometry was optimized, the CAD designs were also optimized to sustain the loads and fatigue that it would experience. Through strict engineering control, we were able to safely optimize parts to a very, very tight factor of safety so that they could be as light as possible. All components were made out of 7075 T6 aluminum or some composite rods. This created the best optimized and by far the lightest suspension that the team has ever created. Now, as you saw in all of the previous slides, every single subsystem within the car was very, very deeply thought out and was optimized to the best of what it could be. But there is no point in having amazing individual systems if they don't work together. Just as important is designing each system to interface with one another and complement each other. The aero team needs to work with suspension to make sure there's enough clearance within the aero body for the suspension geometry. Suspension needs to work with chassis to make sure all of the mounting locations are at the exact right location and strong enough. Chassis needs to work with electrical to ensure accommodation for the wiring throughout the car. And electrical needs to work together with aero just so to ensure that the right formation of solar cells can be fit on the top surface of the vehicle. These are just some examples, but as you can see, this creates a very complex web of interfacing that all needs to work perfectly. Even one mistake can stop the car from competing. To make sure that the systems engineering and interfacing happens flawlessly, we need to employ various measures of engineering management. I will now hand over to Brad, who will go to more detail about this. Thank you.
Awesome. Thanks for that insight, Divyam. And before diving too deep into management strategies we use, I just wanted to reinforce the importance of clear and well-defined values. So after the 2019 race cycle, our team saw big changes. Unfortunately, lots of our members had gone on to roles in their desired industry, but it did leave us with a skills gap. So we worked hard on recruitment and were able to pull together a team of brilliant minds. And the first thing we did as a team was define our values. And this really set the foundation for culture in which we work. A strong set of values serves as an anchor point when you feel like the world is spinning around you. Times often get tough when trying to design, build, and race a car in less than 18 months. But our values give us important perspective and help us regroup and focus on the things that truly matter. So here's something else we believe to be an important foundation to any team looking to achieve something great: a well laid out and clearly defined operational structure. And this is important for many reasons. It gives everyone involved a clear sense of identity, and it shows them how their contributions tie into the big picture. It also helps streamline work when your team members know who they can reach out to for help. So many things we do are learned along the way, and we're operating at the leading edge of technology and are often required to innovate to progress. In a fast-paced environment, or any environment in fact, it is essential to have an archive of knowledge. And there's many different solutions out there, but we've found using the Google Suite works well for us. We've set up a Google Drive to store all of our vehicles' finalized components in a parts library, as well as previous iterations of them, so we can take a step back in time whenever we need to. File management is vital when you're creating a product to ensure ease of access between team members. Also, to ensure you're sending out the right files for manufacturing. It's very important. Naming conventions also play a big part in file management, and we have an Excel library to make this more comprehensive for anyone on the team to find what they're looking for. Slab is a great piece of software too, and it's what we use for knowledge storage and storing documentation. It's essentially an internal Wikipedia for our team. Every sub-team is broken down as per the operation structure, and everything is labeled in a specific way to make this system easy to navigate. And both of these tools are also critical for our succession planning. It might sound cliche, but communication is key to success. There are many different types of communication. Verbal, virtual, and constructive criticism are key players for us. The team uses Google Chat as part of the Google Suite to communicate virtually. During the most recent lockdown, this was essential to our progress. Google Chat has been very useful. You can group conversations and even search using the search function within the app if you need to do that. Design reviews also play a big part in communication. They act as a platform for constructive criticism and feedback. We have a roundtable policy, and no criticism is bad. In fact, it's very welcomed and encouraged as long as it's constructive. And we have three main types of design reviews. So we've got an internal one, an academic one, and also external ones. So for the internal design reviews, they force us to communicate about what's important with focus. We start the cycle as a team and finish it as a family. So naturally, we can get consumed with office banter. Academic design reviews not only strengthen our partnership with Western Sydney University, but also give us great academic insight. And external reviews give us the chance to run our designs past people with a very niche skill set. So the last thing to talk about here is our requirements matrix and also trade-offs. And this has been, if not one of the most important things when ensuring what we're building is fit for purpose, safe, and also competitive. So what you see on the right is our requirements tracking document. It allows us to extract the race regulations into an organized system and add our own requirements, which we believe to enhance our vehicle. This is our engineering Bible, and we can tie the requirement into our parts tracking library, see the rationale behind the requirement, define its priority, see who created it, and also know how we can validate the requirement once we believe it's been met. We have a comprehensive guideline on how to use this matrix so anyone in the team can understand it. Finally, we have our trade-offs. And at the start of 2020, we decided on some key aspects of the vehicle we believe to be critical. We then ranked them as a team, and this now influences every decision we make, engineering or not. So those trade-offs are safety, reliability, performance, working hours, and cost, ranked in that order from high priority to low. Safety's first. We really want to ensure that everyone finishes the race in one piece. Reliability is ranked second and higher than performance. So we rather have a car that runs slow but consistent instead of one that's fast in short bursts. before breaking down. Performance is third. Although our team believes reliability is more important, we still obviously want a strong performer. Work hours and cost are ranked last because they're variables which are more easily controlled. So that marks the end of our deep dive into TED 3 and also the management strategy surrounding. So Divyam and I really hope we've given you some good insight. And if you'd like to know more, please use the details up on screen. We'd also love to hear any questions you may have. So Kartik, I'll hand over to you, mate, to kick off the Q&A.
Yeah, I've had some great questions DM'd to me, but one of the first questions I got was, how long did it take to build TED 3?
Yeah, so I'll just talk a bit about that. So the overall cycle, we get about 18 months from the time the regulations are released to racing the actual vehicle. So in terms of manufacturing and building specifically, we really get about a 3 to 4 month window to complete everything, which is a big task. So hopefully that answers that question.
Yeah, that's great. Another question, we might go to Divyam for this one. Why did you move from your wider cars, TED 1, TED 2, to a much thinner car and a much bullet shaped, as you said?
Absolutely. And the main driving factor was our move to gallium arsenide cells. Now, these solar cell chemistry are much more expensive, and the team previously didn't have the capability to use those on our cars. But for TED 3, we were able to use them, and as they are much better, we were able to, we took the opportunity to have them on our vehicle. Now, gallium arsenide cells, since they are much more efficient, the regulation necessitates you to use only up to 2.4 square meters of it, whereas the silicon cells that we previously used, we were allowed 4 square meters of them. So given we only had to fit 2.4 square meters onto the array, the entire car could be smaller, because really the car shape is often, determined by how much solar collector area that you need to be able to fit on top of it. Because of the lower area as well, we were able to experiment with new configurations, like having an internal chassis going for a much tighter track and wheelbase. And the advancements that we've made as a team in terms of what we can do in-house has allowed us to, push for much more, challenging designs to execute, which, at the end have developed a better car. Hope that answers the question.
Yeah, that sounds real good. Another question that we've got here is, what design elements, if any, from TED 3 are you likely to use on future cars?
I'll have a think about this one. I don't know if Brad can jump in with any.
Absolutely. So I'll provide a brief answer to that first. So, I think with TED 3, a few key design and manufacturing things that we did and developed, will definitely flow across into new vehicles. So an example of that is our trailing edges. Now, if I lose anyone here, just let me know. But when you're laying up carbon composites into a mold, especially into an airfoil profile like what's seen on the aero body, the tail of it, or the trailing edge, is an extremely sharp and pointy surface. So when you're actually pushing the fibers into the mold, it's extremely difficult to get them to conform at that point. So one thing that we learned was, how to make that process better and how to ensure that we did have a sharp trailing edge on our vehicles. So essentially we came up with a method where we only laid up to a radius at the rear of the vehicle instead of trying to lay the carbon weave into that sharp corner. Then we were able to coat the composite part in a special substance, which helped the 3D scanner we used pick up datum points. After that, we imported that file into SolidWorks, our CAD program, and 3D printed a sharp trailing edge that we then figured out how to graft onto it. So I think, that is probably one of the biggest things that I learned that'll definitely be carried across to future vehicles. Divyam, I'll hand over to yourself now.
Yeah, I think that answer also probably gave me an idea of what to say. But the TED 3 was one of the first times that we were able to manufacture so much of the composite work and the actual chassis and aero body in-house. And doing that obviously involved a lot of trial and error because it was the team's first time attempting it. Which meant, figuring out how to, make appropriate tooling, how to, what surface preparation techniques you need, what sort of release agents you need, how do you cure a part that big. We ended up designing an oven made out of a shipping container that we can use to cure the entire part. And so all of those manufacturing tricks, we obviously the car design will probably be different, but the procedures with manufacturing it, a composite chassis or a composite aero body, and the ability to do it in-house is something that we really think will be carrying it over to all of our future vehicles.
Yeah, definitely. Lots has been learnt and lots to keep improving on. Another question we've got: with so much change of team members from one event to the next, how do you bring new team members up to speed and get them to the level of where the team is operating at the current point in time?
Yeah, so that's a good question. And I think, one of the key things which I touched on in the second half of that presentation was knowledge storage and file storage. So, previously we had some amazing team members that had, a lot of knowledge to give. But, unless it's well documented, it's hard for that knowledge to then, pass on to new team members. And if you don't have content and knowledge to use to train them with, then it's quite difficult. So, I would say having that robust knowledge storage system in place, having that great file management system in place. I think they're probably the two biggest things, as well as having a clearly defined operational structure in place that help with that.
And I think the culture within the team is one of learning always. We expect new members to come in without knowing how to build a solar car. That's a very reasonable assumption to make. People who start off on the team, are quite often first year university students, sometimes even high school students. And so the lifespan of a team member, it always starts off with being young and like that, to learning things through older members, and then eventually teaching those skills back again to some of the newer members. And so we have a very strong alumni base and mentors of the team who, are no longer active members, but are always there to help support the new members and get them up to speed and pass on their knowledge.
Yeah, that's real good to hear. Another question, we'll go to Brad for this one. Are teams of designers and engineers separate, and how many are there? I'm guessing how many are in our team at the moment?
Yeah, so at the moment, we've got about 20 active members, but those that are doing specifically design or engineering, it's around 12. So, quite a healthy number. And in regards to, if they're separate, not really. It depends on what they're doing. And I think, the key thing with our project is the fact that, if someone designing the aero body, for instance, Divyam as an example, has a question for someone in the suspension team, wondering if what he's designing will be able to package and fit the suspension components, he can just walk over to the people that are designing the suspension and ask them straight away. And, I guess that's something that's not really common in a lot of bigger companies. So it's quite valuable experience to be able to have that.
Yeah, that's awesome. Divyam, I might go to you for this one. At what speed do you get with a 400-kilometer battery?
At what speed do you get 400 kilometers on the battery? So I think this would refer to, I think we said the car can go a certain distance on the battery pack alone. I think that measurement would have been taken at around the sort of cruising speed of the Bridgestone World Solar Challenge, which for most teams is around 90 kilometers an hour.
Yeah. And we'll go to you for this one as well, Divyam. But the question is, it's very intense to be able to build a car in such a short time frame. But how do you go, working as a team, considering a lot of things you would have been through trial and error for you guys?
Yeah, no, that's a great question, and it is very intense. And I think the main thing is, that the team is about building the best solar car possible. But I think even more important than that is, everyone needs to understand that this is more than anything a learning experience for a lot of young engineers. We want to be able to innovate. We want to try new things. And as part of that, we understand that there will be times where we make mistakes, that there is trial and error, and then there are failures. And the important thing is to, account for that in our time frame. When we set timeframes for different parts of the project, we never estimate that it will be perfect in the first go. You got to leave some time to account for multiple trials, especially for parts that you've never done before, or sections that you've never attended before that are quite new. And through that, I think we're able to still try new things, make mistakes, and still get a car done in the required time frame. But at the end of the day, it does get intense, and that's kind of the fun of it.
Sounds like you're enjoying your experience with the team. Another quick question that we just got: did you get much sleep whilst designing the car?
I think Brad can answer that a lot better.
Yes and no. It really depends on what stage of the design and build phase we're up to. So, one of the things that can be very time consuming, aside from, the obvious like manufacturing and the physical work, is optimizing components. And, it's one of those things that you're never truly happy with how optimized a component or a part or a system is before it goes into manufacturing. So, you can get really caught up and just keep chipping away at optimizing. And that's when you really start to lose time and sleep as well. So, that is one of the many reasons we've implemented those list of requirements. So that way we have, a fixed point at which we know when to stop to manage things like that, and make sure that we all get some sleep as well, importantly.
And quite honestly, I think sleep is one of those learnings from past cycles that we want to improve on, because it is very, very odd what a lack of sleep can do to someone's mind. Decisions that you think you make while being deprived of sleep are quite often phenomenally bad. In terms of you in the moment, you can quite often think everything is going fine, but when you take a look at the bigger picture, or after you take a nap, you get the realization that pretty much none of the work that you do when you're sleep deprived is any good. So it's much better to stop, take a break, and then get back to it afterwards.
Yeah, definitely something we're actively working on as a team. Brad, we'll go to you for this question. Who are some of your alumni, and where are they now?
Yeah, so we've got a fantastic list of alumni that we are pretty proud of. We've got Jay Manley, of course, who was one of the founding members of the Solar Car team back in 2011. And shortly after his time on the project, he was recruited to Tesla to work as the manager of mechanical design. We've got Tony Bazuri as well, who's a fantastic guy who owns APD, so Advanced Power Drives. They're working on some, awesome drone technology, which is really cool. We've got Samuel Bashar as well, who's still, heavily in contact with the team that does help out. He's one of our great alumni mentors. And again, he's working over at APD with Tony on some pretty cool stuff. So yeah, we've got a long list of them. And if you check out our website shortly, we should have some information up about that if you want to know more.
Yeah, we do. And one final question, we'll go to Divyam from this one. How do all the different solar teams come so drastically, from different design angles and different goals? But they meet at the regulations. What aspects of the Western Sydney solar team do we prioritize and that other teams may not?
That's a really, really complex question, and one there's a lot to unpack in that one. I think the team has and always has and probably will continue to put a lot of emphasis on aerodynamics. We've understood how important, how much of the car's performance is contributed through the aerodynamic design. And that's always played a very big factor. And that's not to say that, other teams don't consider it to be a very, very important factor, but it's one of the most important in our design. Something that I think we could instead, focus on more to learn from other teams is the reliability side of it in the future. Moving, focusing on making the car last a long time and reliably, especially we're competing in the upcoming Aussie Solar Challenge, which is a track-based event. And so our car is going to, struggle in comparison to a lot of the competitors because it's designed for, performance and to be light and to be as aerodynamic as possible, and not necessarily to be able to, take 2 full days of absolute abuse going around a track and braking and accelerating and cornering hard. And so, reliability we found needs to probably be something we learn from other teams and focus a bit more on.
Yeah, that's great. Well, yeah, thanks guys for that awesome presentation on TED 3 and our engineering management. But yeah, thanks everyone for coming. We'll probably call it there since we've got no more questions in the chat. But yeah, it was great to have you all, and you can catch us later in the day for more sessions. You can find those details out on our website. But yeah, thanks all for coming, and hope to see you throughout the day.